Hello, CNBT 1311. This is chapter 2. This will be multiple videos also. Here's everything in chapter 2. It's 30 pages. And it goes over all kinds of stuff. The building systems, building codes. You can read this. You're supposed to have a book. I put these first 3 chapters because I have a PDF of the 4th edition. The 5th and 6th editions are different than the 4th. They've had a couple of things added, as we saw in a previous video. All right, the building. Let me reduce this so we get a full page of it. Okay. Now, the resolution from this scan might be hard to read. Use the full frame version in YouTube. Again, these first 3 chapters are a gift from me to you while you get your real book. Then you can go along in your book. All right, so we have the building. Okay. This talks about the definition of scale, proportion, functional zoning. We've talked about zoning. The primary physical building. Now, there is an old architectural phrase called the form follows function. Mies van der Rohe, a German architect that came over here when the Nazis were getting stupid in the 30s, was a big form follows function guy. Less is more was another thing that he followed. Of course, that guy built an all glass house. I don't know about you, but I take a shower and get dressed and do weird things in an all glass house. But everybody thought it was cool. All right. But they gravitated from some of the more elaborate style of Victorian architecture into the modern style, and the form follows the function. Now, that's why most houses are rectangular. Most buildings are rectangular. Because plywood and sheetrock's rectangular. We buy our land by the square foot, and that sort of thing. All right. So, of course, the building has a roof, a structure to hold everything up. It's got vertical, we call this stairs, vertical transportation for humans. We've got a floor plan. You may have a basement, which is a building underneath the building, etc. The primary interest to us in this book is right here. It's the physical systems that define, organize, and reinforce the perspective. And the perceptual and conceptual ordering of a building. So, of course, all this we expect you to read. This is kind of the menu of where these systems are. Okay. Roof systems in chapter 6, moisture and thermal is in chapter 7. We'll talk about the perfect wall and perfect roof. I'll be giving you videos to watch. Floor systems is in chapter 4. Special construction is in chapter 9. Doors and windows are in chapter 8. Mechanical and electrical systems are in chapter 11. And as an architectural designer, you need to understand the concept, but not the engineering. This is going to be your HVAC, mechanical, and electrical engineers that will do this for you. You'll hire them, just like your structural engineer and your soils engineers. Wall systems is in chapter 5. Finished work is in chapter 10. Finished work is cabinets inside the structure. Cabinets, built-in furniture, that sort of thing. Foundations is in chapter 3. The building sites in chapter 1. We've gone through that, and this is notes on materials is in chapter 12. All right. The structural system is just it. It holds everything up. The whole building is a structural system. Walls, roof systems, ceiling systems, um, the enclosure system is what encloses the structure, which is everything else also, right? The walls, the roof, the windows, the doors. You have exterior walls, interior walls. You got load-bearing walls and non-load-bearing walls. And depending upon the type of the structural system, you can use your structural system as a part of your architectural design, like the Centre de Pompidou in Paris, France, where the HVAC system and structural system is exposed, and they used it as the architectural element of the building. Now, some of the French think it's a blight, but some French think it's cool. The enclosure system is your typical wall systems, what encloses the structure. And then there's micro enclosures, those that are inside, separates the bedrooms, and that sort of thing. This talks about your roof, your exterior walls, your doors, and your interior walls. Mechanical system. You got to have a mechanical system. You've got to have plumbing. You got to bring potable water into the building. You got to take wastewater out of the building. Toilet systems, where you're going to run your water pipes. And then your vertical transport systems is elevators and stairs to transport people. Now, if everything's a single-story structure, then that makes it easy. But if it's a multi-story structure, and again, we talked about your site constraints, you may not have a choice but to put a 2 or 3-story box on your site. Firefighting systems and structures may also require waste disposal and recycling systems. That would be like for a commercial building where the dumpsters are. How are you going to get the dumpster trucks in there? If you've got the real estate, like out at the Cypress Center, you just throw the dumpsters out in the dumpster bin out in the parking lot. Trucks come in and dump them in. All right, that's enough on that. We go into performance requirements. Well, some of this is pretty self-evident, okay? When you select, assemble, and integrate the various building systems in construction, you need to take into account the following factors. Performance requirements, aesthetic qualities, we want it to look pretty. Regulatory constraints, again, we're back at codes and ordinances. Economic considerations, that's right, there's no free ride. What's this stuff going to cost? Do I really need Italian marble from Italy? Or can I use something that's locally sourced? The life cycle cost. How long is this building supposed to last? Environmental impact. What's it going to do to the environment? Now, that doesn't mean just the exterior environment. We want to conserve energy because we got to pay for that stuff. So, we have the interior environment of the structure, and we got the external environment of the structure. Are we in a super rainy, hurricane-based area? Yes, we are. So we're going to have to look at wind and rain resistance. All right? And construction practices. If you can't get the skilled labor to put in, let's just say you wanted to do an adobe house in Houston. Why, I don't know, but let's just say you did. Well, we're not in New Mexico or Arizona. Now, how many of our skilled workers in Harris County, in Texas, do you think could actually do an adobe house? Not very many. So you'd have to transport your skilled labor in here. Or if you find somebody, a chuck in a truck that says, oh, I can do that, it may turn out to be a really crappy construction project. So you look at your construction practices. What is available in the area? And this goes through everything. This goes through some points. Well, it doesn't go through everything. That was a silly statement. But it does go through some points. What's our time? How much time we got? Inclement weather, construction equipment required, budget constraints, division of labor and coordination of building trades. Because you're going to have everybody on a commercial project, And you're going to have many different trades on a residential project. You'll have your concrete guys, you'll have your plumbers, you'll have your electrical people, you'll have your HVAC people. And when are they coming in there to do their part of the job? Well, if you've got pipes that's under the slab, you got to have the plumbers come in and do certain work before they pour the concrete. And then when the framers get done, when are you going to let your electricians in there to pull the wire? Well, after the building gets dried in, I hope. Plumbers, when are they going to run their piping inside the house? Then the HVAC people, when are they going to run? And where are you going to stick the HVAC units? Do you have the room around the site if you need a high lift crane? And how much area does that crane going to need? So all that's a part of the construction scheduling. So if you're into construction management, you're going to go through a lot of critical path methods and such like that to figure out how you're going to build this project. Okay. Building codes. We're not going to spend a lot of time in this class on building codes. You have common codes, companion codes that go along with it. I'm sorry. You have your model codes. You have your international building code. You'll have a Houston, City of Houston building code. Jersey Village has their own building code. Harris County has their own building code. They're all similar, but they may be a little different. And these large construction companies, they have, and architectural firms and engineering firms, they all have to be aware of the different codes. You'll see up here, National Fire Protection Association. They have a code for fire resistance and how to do how to design your building. From a fire standpoint, you'll have the National Electric Code, International Building Code is the IBC. It deals with the occupancy use, the type of construction, and maximum height and area. Okay. How many fire exits do you need? How many stairwells do you need? What about your elevators, et cetera, et cetera? There's a lot that goes into this. Now, the International Building Code classifies the construction of a building according to the fire resistance of its major elements: structure, frame, exterior and interior bearing walls, non-bearing walls, partitions, floor, and roof assemblies. All right. They go into type 1 building, type 2 buildings, type 3 buildings, type 4 buildings. Type 4 buildings, heavy timber. I did a lot of heavy timber carpentry work when I was in college. Architect wanted a heavy timber looking commercial building, so we did a lot of heavy timber on the eaves that covered the sidewalks coming off of the metal structures. Type 5 buildings, then we have, let's see, and then type 5 is divided into several sections, and we're going to look at a table below. Okay. All right. Type 1, type 2, type 3, type 4, and type 5. And then they have subtypes in the structural frame, bearing walls, non-bearing walls. You've got people in the construction and design industry that spend their entire life just dealing with codes. They become experts in codes. So when an architect begins to plan a project, they start off with what's the use of the building? What's the building going to be used for? Is it a school? Is it a hospital? And you've got firms that specialize in these things. You've got firms that specialize in educational buildings. You got firms that specialize in hospitals, firms that just do low-rise, high-rise, mid-rise. Then you got firms that just specialize in custom residential. All right. The IBC limits the maximum height per floor, firewalls, occupancy separations, fire separations. Like I say, I am not going to read this all to you. It's your responsibility to read this. Examples of occupancy classifications. A is assembly, which makes sense, auditoriums, theaters, and stadiums. B is businesses. E is educational. F is factories. Your site restraints we talked about for a factory. If you're going to do a petrochemical plant, you're going to need a lot of real estate around there. And you probably don't want to stick it in the middle of a hospital district. Hazardous use, I don't know, a munitions plant, okay, that would make artillery shells and stuff like that, dealing a lot of hazardous materials. Institutional, such as hospitals, nursing homes, and reformatories. Hospitals and nursing homes require special design, special infrastructure. Mercantile, those are stores. This is probably the easiest commercial construction you can do. Your strip shopping centers, if you will. And residential, we all live in some kind of residential, something or another, homes, apartment buildings, and hotels, and storage, warehousing facilities. And as we go down this list, you'll see that the building codes would obviously change. For storage, warehousing facilities, you're going to have less constraints. You mostly worry about fire loading and stuff like that. But residential would be dealing with residential people. Mercantile, your stores. You've got to have a back door and a front door. This also has to do with restaurants and such as that. The next time you go out to a restaurant, say if you go to the Vintage, and I use the Vintage a lot because it's a single story except for the office buildings that are two-story, built onto the first floor for some of the area. Look and see what I call the working doors. Okay, you got the doors for the people to go into the business, like the restaurants, and then you got the little side doors that are in between each of the businesses. That's a common hallway where they drag the trash out. Okay. Now pay close attention to the stuff up here because it talks about firewall separations and fire separations for floors. This is all according to your code. Your mileage is going to vary depending on where you're at, what code you're building it under, etc., etc., etc. So many square feet requires certain things. If it's a storage warehouse, it will have its own special fire code depending on what you're storing, depending on the fuel load that you're storing it in there. Automatic fire dampers and ventilators and stuff like that. I did a big warehouse at one time, added on to the Walgreens warehouse as a structural engineer. The codes changed in between the old warehouse and the new warehouse. So we had to bring everything up to current code. Loads on buildings. You need to pay attention to this for sure. We have dead loads, which is the weight of the structure, okay? It would be how much does the finished structure weigh, okay? Occupancy loads can be both dead and live load. I don't really care what they say. You have an occupancy load, which can change. You can move furniture around. Maybe mama wants to bring up some super heavy stuff up here and store it. Okay, then people want to store stuff in the attic. Then you got snow loads. Okay, we talked about snow loading on the slope of a roof. You got rain loads for ponding. Okay, probably confusing you here. Okay. All right, there we go. We'll break that off. Let me slow down. I'm going too fast. Been too much coffee. Okay, snow loads. Well, we don't have to worry too much about snow loads down here, but I guarantee you in Crested Butte, Colorado, you do. I told you in another video about the snow and the ice sloughing off the roof and killing a lady. The last time I was up there visiting my son cross-country skiing. All right. Your building codes will specify the minimum uniformly distributed loads. Rain loads. If you got a piece of a flat roof, what did we talk about? I talked about that roof that collapsed because the roof drain up here clogged up and it collapsed the building. All right. Settlement loads. That goes back to our foundation. We have differential settlement. So you got to be careful. If you've got one type of soil over here and you've got another type of soil over here, then your foundation needs to take that into account. This may have to have a big, long, deep pier over here, drilled bottom, and this might just be able to be used as slab on grade. Who knows? Your mileage will vary. Okay. Subsidence in settlement loads, or what we call differential loading in the structural engineering world. Ground pressure. Let's say we have a basement. This goes back to those foundations that we talked about. The retaining walls. This represents the load. The deeper you go, the more soil that's down here, the more pressure you've got on the basement wall, or this is really a retaining wall, even though it's a basement wall. This wall carries all the load from up here down to the footing and the foundation. This shows a little gap underneath here. This may be a floating slab with crush boxes, cardboard boxes they put underneath here to rot. So as the soil expands or water pressure, it has a gap, a place to go, depending on your foundation engineer and your structural engineer. Okay. And again, if you've got water problems, you're going to need a water stop in here to keep, and then you're going to need to coat this wall with an elastomeric membrane to keep the water from wetting this wall and leaching through. Again, this is all a part of the coordination between the architect and your engineers, your civil engineer, your structural engineer, and your soils engineer. Okay. Now to build this, remember what I said? We had to excavate back away. We had to excavate back away. I'm a big proponent to this. I've seen a lot of contractors screw up. Yeah, it's one thing to dig this area out and then put this wall back in, but what happens? You pull all this load off of the foundation, off the existing soil down here. This might actually rise a little bit. Okay, it might expand up a little bit, but then you got to put all this back in. And to do that, you're going to do it in benches. You're going to bench backfill this thing. You just can't throw dirt in there and run a bunch of little feet around there to stomp it down. You got to mechanically compact all of this. Okay. You might use a roller compactor, vibratory compactor, a roller on a machine, hand skid compactors. Run big equipment in here to compact this depending on how big this is. And that's an additional dynamic live load, not just the weight of the soil, but it's the impact load and the mechanical load. It would be a live load that's pushing on this wall. So the engineer has to design this not just for the static loading, okay, not just the dead load of this, but the static load of all this going, this mechanical activity going on to compact the soil, because you want that soil compacted or it's not structural. Now, so we have static load. What does that mean, static? Static is slowly applied to a structure until it reaches its peak value without fluctuating rapidly, okay, in a magnitude or position. Under a static load, a structure responds slowly, and its deformation reaches a peak when the static forces maximize. Okay, now what's a live load? It's any moving or movable loads on a structure resulting from occupancy. Let's say you had 100 people up here doing the breakdancing stuff. Not that I do breakdancing. I couldn't do breakdancing. I can't even barely dance normal. All right. But they're jumping up and down. That becomes a live load, okay? Or a dynamic load. In the study of engineering, you take statics and dynamics. Okay, impact loads are kinetic loads, okay, of short duration due to moving vehicles, equipment, machinery. Building codes treat this load as a static load, compensating for its dynamic nature by amplifying the static load. A good example of this would be a car in a parking garage. These cars come flying in there. Let's say the car weighs 4,000 pounds, but it's moving 30 miles an hour and it slams on its brake. The code will tell you to multiply the dead load of the vehicle by a certain factor. In overhead bridge cranes, when we're designing the structure for overhead bridge cranes, certain bridge cranes, the code required us to not only take what the crane could load, in other words, let's say the weight of the crane and what it could load was 10K. 10 kips, 10K. All right, the code would tell us to multiply that by 2.5 times. The old code did. I don't know what the new code did because I'm not in the day-to-day business anymore, structural engineering. So we would have to design everything for 2.5 times what we're going to lift. So if we said we're going to have a crane and what it lifts is 10,000 pounds, then we got to multiply that 2.5, and that's what we would design the structure and the rails and the foundation and everything for just the crane. Now, if we're also using the crane structure inside this big building that would hold up the building, then we got to add all this other stuff over here. So let's say this was a commercial building and we've got a crane in here. Here's the rails for the crane. And that big bridge crane comes across here. And here's the top trolley for the crane. And there's the hook. Okay. This can go this way. It can go that way, and it can come in and out, right? Come forward and backwards down the length of the building. So all these factors. So this way and that way, it's got to be 2.5 times 10,000 pounds. And then, of course, all that comes back down to the foundation. All right. Dynamic loads. Dynamic loads are applied suddenly to a structure, often with rapid changes in magnitude. Magnitude is direction, okay, and point of application. Under a dynamic load, a structure develops internal forces in relation to its mass, and its maximum deformation does not necessarily correspond to the maximum magnitude of the applied force. Two major types of dynamic loads. Two major types. Sounds like a test question. Two major types of dynamic loads are wind loads and earthquake loads. Okay. I also consider cars a dynamic load when you're designing bridges. So you've got a normal pavement, normal roadway. I know this goes back to civil engineering. And then all of a sudden, you've got this head wall of this bridge. Now this is the bridge. Okay, the bridge goes over a canyon and the car comes along. Well, once it hits this bridge, the bridge is going to have columns, right? So as soon as that car leaves the pavement that's on the ground and it transfers to this, all of a sudden now we've got this sudden dynamic load in this direction on the bridge, and this stuff's going to want to have to resist this movement going in this direction. All right. All right. Now, what about wind loads and earthquakes? What did we just say? Two types of damage. Two types, the two major types, and that's what Ching says. But there are other types of dynamic loading too. Well, let's just deal with wind loads and earthquake loads, because that's mostly for construction, right? Buildings. Wind loads are the forces exerted by the kinetic energy. That just means it's moving, kinetic. Ke is kinetic energy. Oh, I'm going to be a geek again. Okay, and kinetic energy is defined by 1/2 the mass. Don't go running away, times the velocity squared. Wow, wasn't that cool? No extra charge for that. And no, you're not going to get tested on that formula. Okay. All right. All right, if a moving mass of air is assumed to come from any direction, the structural components in cladding, they've got to resist this. Now, we talked about this in a previous video, right? About the windward side and the leeward side. Okay. All right. How this is high pressure over here, and it's trying to push it in. I'm going to huff and I'm going to puff and I'm going to blow your house down. And then the leeward side is suction. It's negative pressure. It's low pressure. Okay. Low pressure. It's negative pressure. It wants to suck the stuff out. Low. Okay. Pressure. It's negative. So this would be positive and this would be negative. And I don't care what the evil math nuns told you in school. There's no such negative numbers are not imaginary. They're just going in another direction. See, this is pushing and this is pulling. All right. And this is a fairly steep roof, remember from our previous video. So on this side, we're going to have a high pressure on this part of the roof. And this part of the roof is going to act like an airplane wing. It's going to try to lift up. Okay, so that would be low pressure. Okay, because as that wind's pushing, it's pushing on this and it's pushing on that. And now when it breaks over and comes over, it creates low pressure and it wants to suck the roof off as opposed to push the roof in. All right, so now wind exerts a positive pressure horizontally on the windward. I just told you that. We don't need to read this. It exerts negative pressure on the suction side. And it talks about the rule of thumb for the slopes of where this occurs. Now, into the building codes, you're going to have wind loading and all kinds of wind design. And the taller the building gets, the skinnier it gets, and the taller it gets, you've got different constraints for wind loading. Okay? Design wind pressure is a minimum design value. Every structure has to have a minimum design value. All right, there's going to be a lot of videos in this chapter. We're already at 35 minutes, but that's okay. If this was a face-to-face course, you would be talked to death, lecture-wise. So you can read the design wind pressure is a minimum design value for the equivalent static pressure. All right. Now, flutter refers to the rapid oscillations of a flexible cable or a membrane structure. You can go to YouTube and look at some old suspension bridges that didn't have stabilizers in them during high winds. There was one up in Washington many years ago that just broke itself apart. It started swinging and swaying in a high wind, and it kept going and destroyed itself. Tall, slender buildings and structures, they have this problem. And you can imagine, if you have a tall, super tall building, and it's skinny, and you got wind blowing around it, let's say a hurricane. All right, you got high pressure on this side, and you got low pressure on this side, and then the higher up you go, the more moments you've got. So this thing's going to be like a piece of linguine, and it's going to be fluttering in the wind like that. Well, not quite that bad, but okay. Well, that's pretty weird. But nonetheless, it'll start to flutter. And if the wind is gusting, it pushes it and then lets it go. That means it's going to go over here, then it's going to go back here, and then if it picks up again, it'll go back over here, and then pretty soon this thing is rocking back and forth. Of course, this is a large exaggeration, but you've got to take this into account as a structural engineer and an architect. But that's where the architects rely on the structural engineers and their license and their insurance and stuff like that. Now we get to earthquakes. Earthquakes, man, your mileage is going to vary. What kind of earthquake is it? Is it an up and down shake? Is it a horizontal shake? Depends on what the plate tectonics do. He talks about longitudinal and transverse vibrations. All right. You got engineers that specialize in earthquake design. Now, we don't have too much. The building codes down here on the Gulf Coast, we're more worried about wind than we are earthquakes. So we haven't had too many earthquakes down here in the history of the Gulf Coast. You get further out west and further up north, you do. New Mexico has an earthquake code. California surely does, and it depends on where you are. Your mileage is going to vary depending on where you're designing, and it will be in your local ordinances and codes. All right, and basically an earthquake generates vibrations. Mexico City is built on an old lake that was filled in. They just filled it in over the years with dirt, compacted, but there's still a lot of water underneath there. So I forgot the year, but there was a giant earthquake that hit Mexico City, and the epicenter focused on that old section of that old Aztec lake that they filled in gazillion years ago. And what it did is it pumped that water up through that soil, and it became a giant bowl of oatmeal. So those buildings that were sitting on that compacted soil, that soil became liquefied, and guess what happened to the buildings? They started tipping over and collapsed and all kinds of stuff. It was pretty bad. All right. This talks about how a building generally acts in an earthquake. Okay. It starts to oscillate. Okay. It develops internal forces. And the bottom line here is, and these are force vectors, there's rotation around the building, it's twisting, it's making it go back and forth. But what it's doing is it's hitting a frequency. Okay, this building is actually vibrating up through the cycle of the earthquake. And if you can design your building to survive the cycle up and the cycle down, then your building will survive. Now, I am not going to bore you by reading all of this, but you have a base shear and you have upper shear, then you've got the vibration of the building that the earthquake generates. We call that a natural period of a structure. Every structure has its own natural period. What frequency of vibration will that structure survive? The taller you get, the more spindly and it changes. Okay, and then different materials have different vibration, frequency, resistance. All right. I'm not going to beat you up too bad about this, all right? But that the building needs to survive the restoring moment, and it needs to survive what I call the initial overturning moment, or the lateral load applied by the earthquake. That would going back to the frequency. Okay, it's got to survive the vibration going up and the vibration going down. All right, now if I can find, what did I do with it? Oh, the pagoda. The pagoda, and I'm going to put this in D2L for y'all under the information tab. 5-story pagodas. Why can't earthquakes knock them down? Wisdom from the distant past. Well, we're not going to spend a lot of time on the pagoda, but basically read through this. It's pretty interesting. It's called the snake dance. The Japanese call it the snake dance. There's this giant freaking pole that goes up through the pagoda, and all the stories are supported off that pole. So and this goes through the geekoid engineering of the fulcrum of the tilt, okay, as the pole shapes. And it talks about the bulls of Columbus. And there is a good section of how a pagoda is put together, a traditional pagoda. And there are your bulls up there, okay, which help dampen the vibration, okay? All right. So this is how the pagodas can survive an earthquake. Because basically what it does, just like I told you in a rigid high-rise building, it's got to resist this frequency coming up. Where's my deal here? All right, it's got to survive the frequency, the vibration in the building that's generated by the earthquake. See this? And when the earthquake subsides, it's got to come back. So that's how the pagodas were designed years and years and years and years ago. And some of these are ancient, man. We're talking about 1,300 years ago. And they survived all those earthquakes. And we know that Japan has tons of earthquakes and hurricanes and tsunamis and stuff like that. This might be an interesting read for y'all. And it could be a discussion. The snake dance and the interior pole. Because it's allowed to move. The structure's allowed to move with the forces generated against it. Okay? All right. That's enough of that. All right. Where are we at on time? Oh, my goodness. We're 43 minutes for this. That's okay. And we're only on page 10. Oh, my goodness. You're probably wanting this old man to shut up. But that's okay. We have a lot to cover. All right. Structures. And if a structural engineer is going to do this for an architect, then why does an architect even need to care? Well, you got to start out with a concept of a building that can actually be built, right? I mean, if you came to a structural engineer, and I've had architects do that to me, you know, back when I was a structural engineer. Well, I've got this great idea and I want to hang this thing out 100 feet, but I don't want any columns underneath it because it'll look ugly. And I'm like, dude, what are you going to make this out of? Unobtainium? We can't go that far on a span that's unsupported. Now, based on your concept, I'll sit down and work with you and we see if we can come up with a compromise. And in some cases we did. Well, in a lot of cases we did. But it takes the collaboration of the architect and the structural engineer. Structural forces, this is all a part of statics. These are force vectors. If I have a force going this way, and I am not going to beat you up with this stuff, okay? You can take statics later. Then I have a resultant force that's going that direction, okay? Now, those of you who have been in construction before, this might start to look like a truss, right? Well, if that was a structural member and that was a structural member, and I had another structural member over here, okay, and this was a structural member, what would that look like? That would look like a piece of a square truss, like an old Pratt truss or something, right? Or a Warren truss, or a railroad truss, all right? And so all these forces would be going this direction, and when they reverse, they'd go that direction. This would be in compression. That might even go cycle back through tension if we had a force reversal. So that's all this is representing. So don't get too freaked out over this. The moment arm is bending. If you ever worked on an engine, you've got a wrench, you got a bolt, you got a bolt. You put a socket on it. And you put your ratchet wrench up here, or your breaker bar, and you put force on here. You put your greasy old hand on there and started twisting it around this axis. That's the same thing as this talking. This is the head of the nut or the bolt. This is your wrench force. This is your wrench handle, and this is the force you're pushing on the wrench. The longer this is away from your center point of your rotation, the more moment you have. Okay? We call that foot-pounds of energy, or Newton pounds, but we'll call that foot-pounds. Foot-pounds. So let's say this was 1 foot. 1 foot. And you're putting 10 pounds of force on the end of the wrench. Then you've got 10 foot-pounds, right? If this was 2 feet, it'd be 20 foot-pounds. Or if it's in inches, then you could do it in inch-pounds. So foot-pounds or inch-pounds. And you might talk to your structural engineer, and they might be saying, well, okay, if it's a structural steel frame, then we're going to have so many foot-pounds of torque on the bolts to erect the structure. But that's a moment. And that's the overturning thing. I talked about moments in the retaining wall video. We talked about moments up here with earthquakes. This is essentially a moment, okay? It's a rotation, okay, in any direction. It could be a rotation. In this case, it's rotating that way. It wants to turn the building over. Okay, wind loading. Let's assuming this wasn't an earthquake, but it was a wind. And this is a tall building, and the wind's pushing on that. Okay, at some point down here is the center of gravity of the resistance of the foundation, and it wants to turn this into your wrench handle, and it wants to rotate this building, okay, just like on your wrench handle, around the center point of the rotation, and it's going to want to make this thing go that direction. Okay, that's all a moment is. Okay. Right. Structural equilibrium. This might be a good place to start the second video. Yeah, we're at 49 minutes, so let's do video 2 on structural equilibrium. Structural equilibrium. 12 to 12. How many pages are in this chapter? Oh my God, there's 30. So if we went, yeah, okay, it's probably going to be 3 like the other one. I'll try, well, maybe even longer, okay, because the structure's got to have a lot of definitions in here. All right, so let's stop it here. We'll stop.